recording from here in Auckland, New Zealand. It's the middle of the night. My name's Robyn, and I'm co-chairing the session with my colleague Mojtaba, and we are both members of the VPHi Student Committee. So in this session, we'll be presenting the VPHi Best Thesis Award in Silico Medicine. And I'm sure you're all familiar with this award, but just in case, the Best VPHi Thesis Award in Silico Medicine is an annual award. The deadline for applications every year is usually around late April, and the applicants' PhD theses are assessed by a committee of independent senior reviewers, and the best thesis is chosen according to a number of criteria, including capacity or the knowledge gap, methodological approach, research outputs, and international integration. So with no further ado, it is my great pleasure to announce today that the 2021 winner of the Best VPHi Thesis Award in Silico Medicine is Francesco Regazzoni. I hope I didn't say that incorrectly. Francesco got his PhD last year from the Politecnico di Milano under the supervision of Professor Alfio Quartaroni. And he has been a visiting scholar at INRIA and at Penn State, and is currently a junior assistant professor in numerical analysis at the Politecnico di Milano. Today, he will be telling us about his project, which is entitled Mathematical Modeling and Machine Learning for the Numerical Simulation of Cardiac Electromechanics. So Francesco, congratulations, and over to you.
Thank you very much. I'm going to share my screen. I hope you can see it.
Yeah, we can.
Perfect, I can see it, yes.
Okay, so first of all, let me thank you again for the opportunity of being here, of giving this talk, and thank you very much for having considered my thesis work for this project. So before starting, I would like to acknowledge once more my advisor, Professor Alfio Quartaroni, and my co-advisor, Professor Luca Dedè. The title of my thesis is Mathematical Modeling Machine Learning for the Numerical Simulation of Cardiac Electromechanics. And first of all, I would like to introduce this talk with the motivation that drove the development of my PhD work. During my PhD, I focused on cardiac electromechanics, which I suppose that many of you are already familiar with. And this is a multi-physics and multi-scale system, including several physical phenomena, among which electricity, biochemistry, protein dynamics, so the generation of force, and biomechanics. And the goal of my work was that of building a mathematical and numerical model of cardiac electromechanics, which is at the same time biophysically detailed and computationally efficient. And as you know, there is always a competition between two different goals. And then the more you try to be biophysical detail, the more you have to pay in terms of computational cost. So what I wanted to do was to find an optimal trade-off between these two competing goals. And this trade-off is particularly evident when you focus on the subblock of mechanical activation. So the subblock that deals with the generation of active force. And the reason is that the physical phenomena behind this process are intrinsically complex. And so also the mathematical models for their description are typically intrinsically complex. And indeed, in the literature, the existing models can be split into families. On the one hand, we have physics-based models, which provide mechanistic understanding, but these models are typically computationally very expensive, typically too expensive for multi-scale simulations. And on the other hand, we have phenomenological models, which have been developed mainly for multi-scale simulations, and they are based on a phenomenological representation, so they are computationally faster, but they are not derived from physics first principles. And so during my thesis, we tried somehow to fill the gap between these two classes of models. So in the first part of my work, we focused on the subcellular modeling. So we try to develop the new models that found an optimal balance between these two aspects. And then in a second moment, we also moved to a second topic, which is that of model order reduction. Basically, our goal was that of further reduce the computational costs associated with the numerical approximation of these models by means of pretty mathematical strategies. And with this goal, we developed a new method based on machine learning. The idea was to generate from the high fidelity model a collection of simulations, and then from these simulations to infer a reduced model based on an artificial neural network by means of machine learning that surrogates the output of the high fidelity model. And then by suitably linking the microscale and the macroscale, so the microscopic scale of fourth generation, the microscopic scale of tissue mechanics, building a multiscale simulation in which our finite element model of cardiac electromechanics is such that in each node of the computational mesh, we place a pre-trained neural network that surrogates the high fidelity model, reaching in this manner an integrated electromechanics model with a very good trade-off between accuracy and computational efficiency. So this was these were the three parts of my PhD work, and will also be the three parts in which the talk will be split. So let's start from the first topic, which is the development of high fidelity models of microscale fourth generation. So first of all, let me give you some basic notions about muscle contractions in case you are not familiar with this topic. So for us inside, muscle is generated inside sarcomeres, which are the basic contractile units of the muscle cells, which are made of two families of filament, thin filament and thick filament. And the trigger of contraction is calcium. So when calcium concentration increases, it triggers a chain of reactions, including troponin and tropomyosin, which are two proteins. So tropomyosin changes the configuration, it becomes permissive, and so the bonding between myosin heads and actin can take place. So myosin heads pulls the filament toward the center of the sarcomere, and the joint work of thousands of heads pulling the same direction causes the contraction of the muscle. So to sum up, so this is the big picture. We want to bridge electrophysiology on one side to mechanics on the other side. So the input coming from electrophysiology is calcium concentration. So calcium concentration triggers the so-called regulatory units made of troponin C and tropomyosin. And this is what concerns the so-called thin filament activation. Okay, so this is the first step of the process of fourth generation. The output of this step is permissivity, so the fraction of tropomyosin units which are in permissive state. And when a unit is in permissive state, then the cross bridges, that is the linking between actin and myosin, can take place. And cross bridges are the actual molecular motors, so what actually generates force. So the output of this second step, which is cross bridge cycling, is the active tension. Then we have some feedbacks from mechanics in terms of strain and rate of strain that acts at several levels. But what do we know from experiments? So which are the experimental characterizations of all these phenomena? So the first basic experimental setting is the steady state. So steady state, you fix a calcium concentration and you measure force. And if you plot the force with respect to calcium concentration, you realize that this relationship follows, so it's well approximated by the Hill law, where we have an Hill exponent, an H, which is typically of the order of 5 to 8. So this reveals a high cooperativity. Also, high cooperativity means that a little increase of calcium leads to a very large development force. And the underlying explanation, which is most assumed by the community, is that this is associated with the nearest neighbor interaction between the regulatory units. Then what happens if you change the sarcomere length? So when you increase the sarcomere length, you have two effects. First of all, the maximum tension increases, and this is due to the filament overlap. And then the apparent calcium sensitivity decreases, okay? Sorry, increases. So the curve shifts to the left. And this phenomenon, which is called LDA, length-dependent activation, is very important for the macroscopic behavior of the heart, but a commonly agreed explanation is not being found by the biophysicist community. Then another setting is that of isometric twitches. So you apply. So you fix the length of the sarcomere constant, and you make the sarcomere contract. And what you can characterize is the dependence of the development force with respect to sarcomere length, which is increases, and also the kinetics, so the relaxation time and the time to peak. And what is observed is that at higher sarcomere length, the kinetics is a little more slow. Then the final two experimental characterizations refer to the fast scales. So in the first experimental setup, which is the force clamp, we apply a force to the specimen. So we let the system reach a steady state, and then we apply stepping length. Okay. Then we observe three different phases. First of all, an instantaneous response to reach L1, then an exponential recovery to a length L2, and then a constant shortening with the constant velocity V. And if you plot this velocity against the developed force, you find the so-called force-velocity relationship, which has been first observed by Archibald Hill in 1931, and he won the Nobel Prize for this kind of studies. And this is one of the most important characterization of muscles. So if we want to develop a model for cardiac muscles, we need our model to be able to replicate this phenomenon. Then the length clamp experiment is somehow the dual. So you control length and you apply force. And also in this case, we have the three phases. First of all, the instantaneous response to a tension T1, and an exponential recovery to a tension T2, and then a plateau. And if you plot a couple T1 L1 and T2 L2 on a plot, you find two curves like these ones. First one being associated with the elastic response, so to the elasticity of the myosin arm, and the second curve associated with the rearrangement of the myosin heads. Okay, so to the so-called power stroke. Okay, so try to give you a very brief introduction to the basic notion of muscle physiology. So now we can move to the models that we proposed, and which are of course based on what I presented you so far. So for the development of our models, so we started from the first step of the fourth generation process, so the calcium-driven regulation of the thin filament. And with this goal, we started from the state of the art for this kind of models, which are Markov chain models. So we consider an array of, say, n more or less 30 regulatory units, and we describe each regulatory unit by 4-state Markov chains according to the state of troponin and tropomyosin. So troponin can be either not bound to calcium or bound, whereas tropomyosin can be either non-permissive or permissive. Okay, so this kind of Markov chain has been adapted from pre-existing models, such as the one of Rice and Vacchio. But in this Markov chain, there is still one missing ingredient, that is a cooperative. As a matter of fact, as I mentioned, the cardiac tissue is highly cooperative to calcium. And to model this, so to include this into the model, we need to modify the Markov chain. And with this goal, we adopt the strategy proposed by Rice, which is that of assuming that the configuration where two consecutive tropomyosin units are in different states is energetically less favorable than the configuration where two consecutive units are in the same state. So we call delta G the energy gap in terms of free energy that you have to pay from go to one configuration to the other. And then a basic thermodynamics consideration ends up to modify the transition rates by introducing these factors gamma, okay, that modify the transitions between the non-permissive to the permissive configuration. And thanks to this choice, now the model is able to embed cooperativity. And this explains how a little increase of calcium is able to lead to a very large and quick development of force, which is very important at microscopic level to allow the heart to develop force in a very fast manner. However, there is a price to pay here. And the price is that now the Markov chains are not uncoupled anymore, okay, but they're all coupled together because we have these nearest neighbor interactions. And so we have a unique gigantic Markov chain. And indeed, if you do the computations, the total number of elementary states that you have in this Markov chain, it is of the order of 10 to the power 19. Okay, so if you try to derive the Kolmogorov equation, that is also known that the master equation, that is the equation ruling a time evolution of probabilities of this Markov chain, it ends up that you need thousands and thousands of petabytes of memory only to store the system state in your computer memory. So a direct simulation of this equation is not affordable. Okay, and for this reason, people typically use a Monte Carlo approximation for the simulation of models belonging to this family. However, Monte Carlo method is very inaccurate, very slow to reach statistical convergence, and so we try to look for a different approach. So starting from this model, this is our approach. So we decided to focus on triplets of regulatory units, okay? Not on the whole chain, but on a triplet. And if you consider a triplet, okay, each triplet has 3 units. Each one can be in 4 states. So you have 4 to the power 3 states for each triplet, times n minus 2, which are the number of triplets. So in the end of the day, you have less than 2,000 variables, okay? So instead of 10 to the power 19, we have only 2,000 variables. But now comes the challenge, which is that of finding the equation for the dynamics of these triplets. So to fix ideas, we consider a sample triplet like this one. Then we consider all the possible transitions. So first of all, the central proponent can change state. So for being bound to calcium can be unbound to calcium. But for the transition rates, we have all we need. Okay, so they are defined by the cooperative Markov chains that I introduced in the previous slides. The same also for the troponin units located at the outer units of the triplets. Then concerning the tropomizing units associated with the central regulatory unit, also for this we have all we need to compute the transition rates, because we need the neighbors, but we know the state of the neighbors. But what about ones located at the end of the triplet? Okay? So let's focus, for instance, on this one. To know the transition rates of the tropomizing, we need the states of the neighboring ones, okay, because of nearest neighbor interaction. But we don't know the states of the one of the units in position 4. Okay, so we have these 4 transition rates highlighted in orange, which we don't know. Yeah? So we need to find some closure relationship to characterize these transition rates. And to find this closure relationship, we introduce an assumption. In particular, we assumed that at each time, the units at distance 3 are condition independent given the units located in the intermediate position. So this is a quite technical assumptions, but from a modeling viewpoint, what is saying here is that the 5 units, they are not independent. On the contrary, they are highly correlated. But what we are saying that the correlation is mediated by the intermediate unit, which is coherent with the Thesis Outline model. Okay, so we can see that this is a physically motivated assumption. And most of all, thanks to this assumption, we can write in exact form the missing terms. So in the end, we can write in closed form an equation deriving the evolution of the probabilities of triplets, where at the right-hand side, we have only probability of triplets. So everything is written in closed form. So we end up with this system of nonlinear ODEs with less than 2,000 variables, which is so computationally tractable, which includes an explicit representation of end-to-end interaction. So and nothing is has been transformed to a phenomenological description. But we have a question here. So is this accurate? So introducing assumption which is physically motivated, but is this accurate with respect to the original model? And to answer these questions, we perform this numerical investigation. So we reduce the number of units. So we consider just 6 units so that we can find numerically in reasonable time the solution of the full Kolmogorov equation. And we compare the results with the one obtained with our model, and we obtain a very, very good approximation. And then we also compared the results with the ones obtained with the Monte Carlo method. And it turns out that to obtain the same degree of accuracy that our model provides, but with the Monte Carlo method, we need 72 hours of simulation, whereas with our method, we only need 16 seconds. And also the number of variables decreases from 10 to the power 5 to 10 to the power 3. So we have 4 orders of magnitude of speed up with respect to the Monte Carlo method, which is the gold standard for this kind of models. And what about the numerical results? We also prove that with our model, we can replicate the mainly experimental characterization, including the cooperativity, as we mentioned, and also the LDA. Okay, so this is really remarkable because there is not even a clear pharmacological physiological explanation for this phenomenon, but still with our model, we are able to replicate this phenomenon. Okay, so what I presented you so far concerns the thin filament dynamics, but now we can move to the full structural dynamics. So to this cooperative Markov chain, described triplets of regulatory unit, we also need to add a description of cross bridges, so for the interaction of actin and myosin. And with this goal, we started from a very classical model, which is the model of Huxley of 1957. In which myosin is described as a linear spring, which can be in 2 states. So this is a bistable element. This can be either bound or not bound to actin. And we modified this model by introducing a dependency of the transition rates, which depend on the strain of the myosin arm, but we introduced also a dependence on the permissive state of the associated tropomyosin. So the binding is possible only when tropomyosin is permissive. So in this manner, we couple the thin filament activation and the cross-bridge cycling. So putting everything together, we end up with a Markov chain, which is really huge. And indeed, we have stochastic processes for troponin C, tropomyosin, and myosin. But if you count the number of degrees of freedom, it ends up that you have 10 to the power 60 degrees of freedom. Okay, so this is a very, very large number. So just to fix ideas, the number of particles in the universe is estimated to be 10 to the power 80. Okay, so 10 to the power 60 is a really remarkable number that gives the idea of how complex the dynamics that we are trying to describe is. So we cannot think about a direct simulation of this kind of Markov chain, so we need to look for some reduction approaches like the one that we have seen before. And indeed, we base our reduction strategies on two approaches. The first one is to introduce suitable assumptions like the one that we introduced before, that are aimed at focusing only on first order interactions. So basically we neglect second order interaction, so a high order interaction between 5 units. We only focus on first order interaction, and this allows to partially decouple all these huge number of stochastic processes, and so we drastically reduce the number of unknowns. And then the second approach that we use is that of moving, so departing from the traditional thick filament centered description of cross bridges in favor of a thin filament centered ones. So this is just a change of frame of reference, but this allows to further decouple the coupling of all the stochastic processes. So thanks to these approaches, we end up to a model like this one, where we have a description of the regulatory unit, which is the one that I presented you before, and then we also have equation for the attachment and detachment of cross bridges. And similarly to the Huxley model, we introduce a probability distribution for the strain of attached cross bridges. But unlike the Huxley model, where you have a unique probability distribution, here we have 2 different populations. So the population of attached cross bridges associated with the permissive binding site, and the family associated with the non-permissive binding sites. So we have 2 different probabilities, these distributions. We have 2 different PDEs that accounts for the transport due to the sliding of the filament, and we have 4 sink and source terms that account from the fluxes between the 2 populations. So this is one model of full structural dynamics, accounting for a little less than 2,000 ODEs and 64 PDEs. But in order to avoid having to solve the PDEs, we also employed a trick which is very used in statistical physics and has also been used for this kind of models, for instance, by Bestel and Chappelle. And this trick allows to, so in case a suitable assumption, the transition rates are satisfied. So this allows to focus, instead of the whole probability distributions, just on the first two distribution moments. So distribution moment of order 0 and of order 1. And so by applying this approach, we were able to reduce the PDEs to a system of ODEs. So in the end of the day, we end up with this system, which accounts for 2048 ODEs and 10 parameters. Okay, so this is what we call the spatially explicit ODE model, where spatially explicit stands for the fact that we explicitly describe the spatial distribution of proteins inside the sarcomere filament. And we also propose a second model, which is a reduction of this first model, which is a mean field model in which we consider a triplet, so not a single unit, but a triplet of units located in the single overlap region, that is the region of optimal overlap between a thin filament and a thick filament. And then we account for the effect of filament overlap by means of the single overlap ratio function, okay, which is the function that accounts for the dependence of the length of the single overlap region with respect to the total sarcomere length. So in this manner, we end up with a model with only 20 of these. Okay, so just think to the number of degrees of freedom that we start from. We now have only 20 of these and 11 parameters to be tuned. Now we can move to the topic of how to calibrate the parameters associated with this model. So with this goal, we developed a semi-automatic pipeline, which is based on experimental measurements that are typically available in the literature, which are the ones that I already presented during the first part of this talk. So steady state conditions, isometric pitches, force-velocity relationship, and the response to fast steps. And here the key observation is that all these measurements are associated with different time constants. In the steady state condition with the infinite time constant, isometric pitch more or less 100 milliseconds, and then decreasing to very fast scales. And this allows to decouple somehow the contribution. And indeed, it is possible to prove that different parameters are associated with different time constants. So we propose a pipeline in which first we associate the parameters associated with the fast constants, so with the cross-bridge dynamics in particular. And then, having fixed these parameters, we can move to the parameters associated with the regulatory units. So we employ here a quasi-static approximation of cross-bridges, and then we calibrate on regulatory units. And then we first calibrate the steady state. Yep.
Sorry, Francesco, sorry to interrupt you.
Yep.
You seem to have developed a bit of an echo. Can you maybe quickly double check your mic and your sound settings? It was fine the whole time. And now there's a bit of an echo. Sorry.
Well, if you're used to using headphones, maybe this will have to reduce. Can you hear better now?
No, still echoey.
If anyone has the mic open, please mute yourself, because that might come from an attendee previously.
Okay. Is it better now?
No, unfortunately not. Do I sound fine? Do I sound echoey?
I hear fine.
Okay.
So I don't know. I can check my audio setting. Now, do you still hear echoing?
Yeah, still echoing.
So maybe we can just go ahead. I mean, if it's clear, intelligible.
Yeah.
Okay, sorry about that, Francesco.
No problem.
Sorry to interrupt.
I'm sorry for that. Okay. So we can start from the first stage of the calibration. So this regards the fast case, so in particular across ridges, and we were able to prove that the 4 parameters associated with this phenomena can be linked with the one-to-one relationship with the 4 observable quantities. Okay, so we can invert this relationship, and we developed an automatic algorithm that, starting from these 4 observable quantities, can reconstruct these 4 parameters. And indeed, by doing so, you can see on the bottom of the slide that we can fit very well the force velocity relationship with respect to experimental data, and also the response to process. Then moving to the second part, which is associated with the parameters of regulatory units. We first start with the steady state. So here we have 4 parameters to be calibrated, and here we employ manual calibration and using also some a priori from the literature. And here the process is made easy by the fact that each parameter can be associated to a different effect. For instance, the KD, which is the constant dissociation constant, is associated with the left or right shift of the steady state curves. You can see here that we can fit, also in this case very well, experimental data. And finally, we are left with the calibration of those 2 parameters, which are the kinetics constant for troponin and for tropomyosin. And for this final step, we employ a brute force approach. So we simply sample the parameter space, and we try to minimize the discrepancy between experimental observations and model prediction. And so we find the optimal choice for these 2 parameters. So this is what you can do when you have many data, because we use many data under different experimental settings. But unfortunately, this is not always the case. For instance, when you deal with human cells, it is not easy to have many data, especially at body temperature, since typical experiments are performed at room temperature. So in this case, we propose a 2-steps calibration pipeline. So first of all, we calibrate the model in the case where we have many data, so for room temperature cardiomyocytes, and then we move to body temperature human cardiomyocytes by adapting only those parameters that are affected by the changes in species and in temperature, which are in particular constant sensitivity and the kinetics of regulatory units. And then, as validation, we observe what we obtain for isometric ridges. So these are data that were not used for the calibration. So this is a check that we do a posteriori. And we investigate the dependence on the circular length of the developed force and the kinetics. And you can observe that we have a very good agreement with the experimental measurements. And I'd like to stress that the model has been calibrated for a fixed circular length. So the dependence on the length is something that naturally emerges from the fact that we have used a biophysically detailed description of the geometrical arrangement of units within the sarcomere. Okay, so this concludes this first part, and so before going to the second part, let me ask if you can hear better now. In case not, can you hear neatly now?
I can hear you fine, but you're still echoing.
Okay. If you like, I can change my laptop. It will take just a couple of minutes.
I think if you speak slowly, I can still follow. So I would say it's fine. Yeah.
Okay. So I'll try to slow down.
Thanks.
Okay. So moving to the second part. So far we have, so at this stage we have developed new models for sarcomere modeling, but we want to reduce the computational cost associated with the numerical approximation. And with this goal, we dealt with general purpose algorithms, and we developed a new method. And since this is not targeted only on this method, on this model in particular, in this section I will be a little more general with the notation. So we assume that we start from a high fidelity model, that is a model where we have a state x that evolves according to a differential equation and driven by some input, some time-dependent function u. And in general, we are not interested in the whole state x, but only in a few observables. So we define an output, a time-dependent output y. So in our case, u are the inputs of the circular dynamics, that is calcium concentration and circular length, and the output is the generated force. Okay? And model order reduction in general is a set of techniques that allows from this class of models to derive another model, that is the reduce of the model, which is formally written in the same form, but where the state small x is lower dimensional, and such that the input-output map, so the map from u to y, is hopefully as close as possible to the one of the high-fidelity model. For this, we have basically two approaches. The one is the model-based, so because we start from the high-fidelity model and we project it on a lower dimensional subspace. And the other one is a data-driven approach. So from the high-fidelity model, we generate a collection of input-output pairs, and from these input-output pairs, we try to infer a reduced model. So applications are in many query settings, like sensitivity analysis and parameter calibration, or where you want to reduce the dimension of the model, or this is only possible in the data-driven approach when you want to directly learn a model from experimental measurements. So this is our proposed approach. Let me introduce a little bit of notation. So we denote by calligraphy Q and calligraphy Y the set of time-dependent input and time-dependent outputs. So these are set of time-dependent functions. Then we select a class of candidate models. So in particular, we focus on models described by system of ODEs. And here, the key observation is that given a right-hand side f belonging to a subset of elliptic function, an observation function g belonging to a subset of continuous functions, and initial state x naught belonging to a subset of Rn, these three objects uniquely identify a map from time-dependent inputs to time-dependent outputs. So we define in this manner a class of candidate models, where the right-hand side observation function initial states belongs to these three sets. And so we can rephrase the model order reduction problem as the best approximation problem, where we basically look for the model belonging to the class of candidate models that minimizes the distance between the output of the high fidelity model and the output of the reduced model. Okay, so this can be rephrased as a minimization problem or an optimal control problem, where we are minimizing with respect to functions. So this is a minimization problem in function spaces. So something not really standard. But before dealing with an algorithm for the solution of these kind of models, let we deal with the question. So is the solution unique? Well, the answer is no, it's not unique, and this is due to the fact that given a model, you can always perform a change in the state. Since you only see input and outputs, you get a model that is formally written in a different manner, but the input-output map represented by the model itself is exactly the same. But we can exploit the fact that the solution is not unique, and we can exploit it by reducing the space of the set where we are looking for a solution. So in order to reduce the ambiguity of representation. And we can do that in at least two different manners, which are the ones that we propose. So I will be quick in this part. So in the first case, we fix the initial state, and in the second case, we fix a priori also the observation function. So we are only optimizing with respect to the right-hand side f. But we need one last ingredient, that is how to choose these spaces. So this function space for f and this function space for g. And to derive this choice, we derive the theoretical results, which can be seen as the best approximation for theorem for time-dependent models. So under suitable hypothesis on these functions f and g, so they should be dense in suitable spaces. So we were able to prove that the set of models, of candidate models, is densing the set of all the possible models. So in other terms, given any models described by system of ODEs, we can find one reduced model that approximates it with arbitrary accuracy. So given this theorem, we decided to approximate both F and G by two neural networks. So what is an artificial neural network? It is a function approximator given by the alternate composition between an affine transformation and a given prescribed nonlinear function that acts component-wise. And the fact is that artificial neural networks satisfy these two technical hypotheses. And so we decided to use the neural networks as a corollary of this theorem. We obtained that the space of time-dependent ODEs where the right-hand side observation function is represented by a neural network can approximate within any prescribed accuracy any possible time-dependent model. Okay? So on the basis of this theoretical background, we developed an algorithm to train this neural network. So here the key observation is that the right-hand side of the observation function f and g, they can be written as a function parameterized by the weights and biases of the neural network. So we have moved from a continuous optimization problem to a discrete one. And so we can apply well-known methods. In particular, we employed the joint method to compute sensitivities. So at each epoch of the optimization algorithm, we have to solve a primal system, so forward system, and then the adjoint dual system backward in time. And this allows to compute gradients. And then, given gradients, you can employ basically any gradient-based optimization algorithm. And in particular, we use the Levenberg Markov method. So these are a few benchmark cases to which we apply our method. So this is a classical benchmark model of reduction. This is a nonlinear transmission line circuit, a system of 1,000 highly nonlinear ODEs. We've showed that with our approach, we can approximate this model with an error that decreases exponential with the number of states. Then we move to a G, particularly the heat equation. So here the inputs are the conductivities in these 9 subsets of the domain, and the outputs are the average temperature in these 3 control points. And we compared our approach with the reduced basis method, which is considered as the gold standard for reduction of linear PDEs. And we saw that with our method, we can achieve an approximation which is 1 order of magnitude better, and also a computational time in the online phase, which is 1 order of magnitude lower. So our method is more fast and more accurate than the reduced basis method. And now we can finally move to the application of this method to the model that motivated its development, which is the sarcomere model that we presented in the beginning of this presentation. And so here the inputs are calcium and sarcomere length, and the output is the permissivity. So far, the method that I presented is a black box method, because we are only looking at the outputs of the model. But we can also modify it in case we know something about the model to be reduced, particularly if we have some a priori knowledge. In particular, here we introduced 2 additional terms in the loss function that accounts for the fact that we know, for instance, that the behavior should be cyclical, and the fact that we know the location of some equilibrium. So we move from a purely black box approach to a gray box approach. And by applying this method, we trained our neural network, and we developed this reduced model with only 2 states. So starting from 2000 states, we end up with a model with only 2 states. And we can say at the bottom of the line of the slide, the blue line is the output force of the high fidelity model, and the red one is the one obtained by the reduced model. And you can see that the approximation accuracy is very good. We also validated the results with respect to the high fidelity model, and we obtained an overall testing error of less than 2%, with a speed up of more or less 4 orders of magnitude. And also we tested the long-term response to see whether our model were able to to behave well also on a longer time horizon than the one used during training, and the test was successful. So now we can move to the last part. In the first part, we have developed some models, and then we have developed a strategy to accelerate the numerical resolutions, and now we can put everything together and build a multiscale electromechanical model. So what we want to do here is to bridging the scales. So on the one hand, we have the microscopic scale, we have the elastodynamics equation, which is a deterministic model. And on the other hand, we have microscopic force generation, which is on the other hand a stochastic model. And we have stochastic fluctuations, which are not negligible. Indeed, the stochastic fluctuations are normalized with respect to the mean are of the order of 25%. So we have to ask ourselves whether these stochastic fluctuations affect the macroscale. And to answer these questions, we developed a mesoscale model, so a chain of half sarcomere. We have, first of all, a parallel arrangement in half sarcomere, and then a series arrangement to build a chain of sarcomeres. And by some computations, we were able to prove that thanks to this parallel arrangement, there is a sort of compensation of the stochastic fluctuations, and so the fluctuation at the level of half sarcomere are of the order of 10 to the power -3. So we can assume that they are negligible. So in this manner, we have proved that the homogeneous solution where in a given region of space all the sarcomeres are elongated in the same manner is a good solution of this mesoscale model. But we need to answer a second question. So is this solution also a stable equilibrium? Because if this was not stable, then any little fluctuation will lead the system out from the equilibrium and lead to some instabilities like buckling instabilities. But we want to avoid this. And we proved that at least in the working rate of sarcomeres, this solution is also stable. And so we can assume that the elongation of the sarcomere in a given region of space can be computed as the reference length times the average strain, the average distortion of that region of tissue. Okay, so by incidentally, this is not true outside the working range of sarcomere. So, for instance, if you elongate the sarcomeres too much, this is not true anymore, and so you can have some buckling instabilities. But at least in the normal working range of sarcomeres, this is also true. So we can finally formulate our integrated cardiac electromechanics model. So at the center, we have our sarcomere dynamics model, where we have states that evolve according to calcium concentration, sarcomere length, and its time derivative. And this is coupled on one side with electrophysiology, which provides calcium as an input, and on the other side with the equations of passive mechanics, which provide sarcomere length, which is computed from the tissue strain, and the output of the sarcomere model, which is the active force, is inputted, so this is a feedback to the mechanics model. So giving a little more detail, we describe electrophysiology by means of the model domain equation, which is a system of diffusion reaction PEs, coupled with an ionic model, in particular the 10-Tascher Pamphilov model, which is a model describing the biochemistry of cells, so the fluxes of ions, the opening and closing of voltage gating channels, and so on. And concerning the biomechanics, so the tissue mechanics, we consider the elastodynamics equation with the Guccione strain energy density function, and we introduce a near incompressibility constraint to account for the quasi-compressibility of the system. So this is a real-time solution. Here you can see the tissue displacement. Here, the fibers architecture, which were generated by means of a rule-based algorithm. This is a final comparison of a validation of our multiscale model, wherein we use the neural network-based reduction model with respect to the high fidelity one. We can compare compare here the main biomarkers. For instance, this is the PV loop. The dashed line is the one obtained with the neural network model, and the solid line, the one obtained with the high-fidelity model. You can see here the accuracy in the main biomarkers. We have an accuracy of order 10 to the power minus 4, 10 to the power minus 3, so very good accuracy with a computational speed up, which is also very good. So the subblock of activation is decreased by 400 times, and overall with a speed up of 10 times. So we switch from 20 hours per simulation to only 2 hours for simulations or 20 cores. And also the memory usage has been drastically reduced. So to conclude, I would like to quickly show you some recent development that we had after the end of my thesis. So now we have also coupled our electromechanical model to a zero-dimensional parameters model for the external circulations. And this allows to compute not only the pressures and volumes within the left ventricle, but also in the other compartments, and also to provide the left ventricle simulation itself with more physiological, meaning closer relationship between pressure and volume. And for instance, this allows to investigate the effect on the heart mechanics on changes in the external circulation. For instance, you can investigate the effect of running the preload, the afterload, or the contractility. You want to study pharmacon or some disease, you can use this approach. In particular, here you can see that our model is able to reproduce the so-called frame-starting effect, by which, for instance, if you increase the preload of the left ventricle, you will observe an increase in stroke volume. And this emerges from the macroscale, because the microscopic basis is in that LDA effect that I mentioned at the beginning that our model is able to replicate. So the fact that the macroscopic scale we can observe the frame starting is due to the fact that the microscopic scale will have a good description of circumdynamics. Then we can also generalize it instead of having a single ventricle to 2 ventricles, and this is the result of the first simulation that we got with 2 ventricles. So to conclude, we have developed 2 models, trying to find a good trade-off between biophysical accuracy and computational efficiency. We were able to show that our model, we predicted the main features of process generation, so the state, the process relationship, the LDA, and so on. We have also proposed a novel non-intrusive approach based on machine learning to reduce the computational complexity of a time-dependent model. And by means of these methods, we reduce the computational cost associated with the electromechanical simulations by more or less 1 order of magnitude. And can say that the physiological goodness of the output of our model makes them promising for studying the pharmacological action of pharmaca, or to investigate the effect of particular diseases. So thank you very much for your attention. If you're interested, you can find more details in these publications. And if you're interested, you can also find implementations in MATLAB, Python, and C++ of the proposed models and proposed methods in these GitHub repositories. So thank you again. And in case you have questions, I will be happy to answer.
Okay, thank you so much, Francesco, for this very detailed presentation, very technical one. It was indeed very impressive. And yeah, let's wait for a couple of minutes for people. But yeah, we're supposed to have a break at 3:10. But yeah, we have still time for a couple of questions. So you can type it in the chat, or just turn on your microphone and ask if you have any special question. So Jerome, yeah.
Yeah, thanks, Mojtaba. People are shy, so I will start. Thank you, Francesco, and really, really impressive work. My questions are a bit of curiosity, and I don't know. I hope I haven't missed anything. But when you, so if you need to personalize then your model, so actually the physiology described by the ODs, so has to be perturbed. The geometry has to be perturbed probably too. And how much need do you have to relearn in order to have a patient-specific computationally efficient model? So do you have to go then through the whole learning every time you want to apply the model into a specific clinical case? Or do you have already then within your meta model, do you have already then the personalization nodes?
Yeah, so it's a very interesting question and also very tough question to answer. I think that the answer will be different whether you consider the microscopic model or the macroscopic one. So concerning the microscopic model, concerning the training of the neural network, so in the one that represented you, this is done for fixed parameters. So in case you want to change the parameters, you have to retrain the neural network. So this is not universal. However, we also trained some meta models, like you mentioned, that also learned the parametric dependency. Okay, so in this case, you don't have to perform train whenever you have to change the parameters. For some parameters, you don't need to do that because, for instance, the most important one, which is the contractility, only rescales the output. So this is just a multiplicative factor that rescales the output. So in that case, you don't need to train, to learn the dependency because it is given in that manner. Anyway, I would like to notice that the personalization of microscopic models is not very common because you will need personalized measurements at the microscale, which is not very easy. So what we typically do is that we personalize only the microscopic one. And so in that case, concerning the fourth generation in particular, what we only change is the contractility that I was mentioning before. And so we don't need to train again the neural network because we only need to rescale the output of the model by a constant factor.
Okay, thank you.
Okay. Any other question? If not, I have a couple of questions, but yeah, let's see if others have something. So I can go on. I can ask you the first one, maybe. That was related to the first part that we were talking about, the model reduction using set of ODEs. But in a graph that you wanted to compare the efficiency of the ODE system as well as the Monte Carlo simulations, you had also the exact solution, and that was your reference. But I think I missed something, but you were talking about the fact that it is impossible to get this exact solution. So maybe, yeah, that was one of the ODEs, or it was the system of ODEs, or what? I didn't get that.
Yeah, I work quick on that part, so probably I didn't explain it clearly. But to do that comparison, we reduced the number of units. Okay, so typically a sarcomere has more or less 30 regulatory units. Okay, so we have 4 to the power of 30 states. To do that numerical test, we consider only 6 units. So we have only 4 to the power of 6 states. Okay, so in that case, a direct simulation of the full Kolmogorov equation is feasible. So we did that comparison in that case. So we also tried 5, 4, 3 to see if there was a trend, but the approximation were more or less constant, and so we were comfortable that we would have the same result also for higher number of units.
Okay. So exact solution was the analytical solution? And
no. The exact solution was the numerical solution, okay, obtained with the Kolmogorov equation. So it is still a numerical solution, and to get that, we performed the convergence analysis with respect to the time step to be sure that it was close enough to the analytical solution, and then we took it as a reference solution.
Yeah, that's clear. So I still see no question here. So I just take the opportunity and go for another one. I saw you were using the term speed up several times for different scenarios, and especially the time that you were comparing the performance of the neural network with the performance of high fidelity model. You mentioned that the speed up is 10 to the I think to the power 4 or something, but for the neural network it was, I think, with 2 variables. Yeah, the last slide maybe of the neural network. Yeah, this one, 34. 34. Yeah, this one also, but what I mean, slide 34.
This one, 44.
Oh, 34.
Sorry.
Yeah. Yeah, here. And I didn't get, for example, in this case, what do you mean by speed up when you are comparing the neural network performance? And also you didn't mention the number of hyperparameters that you have in the neural network model, and then you were comparing that with the model that was developed in the first stage. So can you clarify what do you mean by this speed up? And then
so here, what we do is the following. So we take the high fidelity model, the one with more or less 2,000 variables. Okay, so this is not the same figure that we had before, because this is a little variation of the model with 2,048 variables. Okay, but basically this is the same model. So we take this model and we perform all these numerical simulations. Okay, the one in color. Okay. And for each simulation, okay, you need more or less 10 seconds, okay, on a standard laptop. Okay, then we take the neural network model and we perform the very same simulation, so with the same inputs, okay. And in that case, for each simulation, you need a few milliseconds. Okay, so the speed up is the ratio between 10 seconds and a few milliseconds. Okay,
yeah.
So this is how we compute the speed up. And then we compare the errors between the outputs, and the overall error is, the relative error is more or less 2%, training and testing. Then concerning the hyperparameters, so the neural network that we trained is this one. Okay, this is not just for illustrative purposes, but this is the true neural network. Okay, so this is not deep, this is not a large neural network. So we have 2 hidden layers with 6 neurons. So the number of hyperparameters is, I don't know, but it could be 100 more or less. Okay.
Yeah,
So we were surprised a little bit at the beginning when we realized that we only needed a shallow and small neural network. So at the beginning, we first tried to use very large architectures, but then we realized that we didn't need large architectures. And maybe here the key is in the fact that the true architecture is not only this one, but you have to, so you have the neural network, at the next time step, you have the same neural network. And so if you unfold the entire architecture, the real architecture is much bigger. So in the end, you have a very deep network, but the basic unit that you train is very small. So maybe here is the key, so why we don't need very large neural networks.
Nice.
And this is also true when we apply this method to PDs, not only for ODs, but also to PDs.
Yeah, makes sense. Yeah, thanks. And we have one question from the attendees. So Benjamin, please go on.
Hi, thanks for the presentation. It's really great work that you've done here. Would you mind briefly going to slide 36? My question has to do with essentially your constitutive model at the macro scale. And I see there, so 36, slide 36.
This one? For this one?
That one, 36, yeah. So I see there you seem to be basing it on your what's commonly called like the fourth invariant, so your deformation gradient multiplied by the fiber direction.
Yeah.
And so I assume that's because your microscale model, it seems somewhat one-dimensional in a sense. So your stress tensor at the macro scale, you essentially just modeling the anisotropic stress. You don't take into account any sort of isotropic behavior of the ground substance. Is it only the fibers that you're looking at?
Yeah. So this is also another good question. So here you can see what is the active stress tensor that we are actually using. That is given by the scalar force, which is the active force, times this tensor. And as you mentioned, this only acts in the direction of fibers. So this was an approximation that we did. We assume that active force is generated only in the direction of fibers. Actually, this is not 100% true. Indeed, or better, this is true in case you know exactly the direction of fibers. Okay. But it is not easy to know the direction of fibers unless you have very good imaging resolution. And typically, what ones do is that F naught is the main direction of fibers, and around F naught you have some dispersion of the direction of fibers. And so what people all typically do is that to add to this term two other terms, one in the direction of sheets, and they are in the cross fiber directions, with a smaller constant, so weighted by a smaller weight to account for the fact that we have also some force in the sheets and in the cross fiber direction. And actually, we are doing this now, so in the final simulation that I presented you, the one with two ventricles, contain that terms, whereas in these simulations that I presented you here, this term was not contained.
Thanks very much.
You're welcome.
Okay. So as far as I see, no further question. So yeah, we can finish the session. Congratulations again, Francesco.
Thank you very much.
For this prestigious award. And yeah, Jerome, the floor is yours.
Okay, thank you very much, Francesco. Thank you, Mojtaba and Robyn. So now it's time for the hands-on. So no break, but good science. So so now you can move actually to your hands-on sessions. So you already have received the Zoom link. And so we meet again at the main link for the poster session at 16:20.